Einstein's field equations define our understanding of gravity and the vacuum. They model a universe where a continuous geometric space interacts with a discrete structural boundary. Within the standard model, the foundational constants governing this relationship, Newton's constant g and the cosmological constant lambda, are treated as empirical dictionary entries. They are values measured by observation and patched into the equations after the fact. This creates a mathematical loop at the Planck scale. Standard physics requires a precise value for both g and lambda to calculate the vacuum energy floor, making it impossible to solve for one without the other. Relying on these patched-in measurements reduces gravity to a measured parameter rather than an understood structural mechanism. An alternative approach begins with a topological postulate. Reality is driven by a global standing wave on a bounded one-dimensional edge, mapped directly into a continuous three-dimensional space. Under these geometric rules, gravity functions as something other than a fundamental force awaiting quantization. Gravity is the explicit geometric interface required to bridge the mismatched topologies of the discrete surface boundary and the continuous ambient space. We can extract Newton's constant g directly from this relationship. It emerges as a strict 3-to-2 exchange rate between the two-dimensional vacuum energy of the boundary and the three-dimensional curvature of space. Deriving g purely from algebra redefines gravity as the precise geometric cost of translating information across dimensional boundaries. Two distinct partners generate this gravitational interaction. On one side is the continuous three-dimensional space. On the other is the discrete Möbius surface acting as a boundary constraint. The space carries curvature as a continuous field. The Möbius surface carries a discrete topological eigenvalue. This specific value sets the vacuum boundary condition for the entire system. The Gauss equation is the sole mathematical bridge capable of converting intrinsic two-dimensional surface curvature into an ambient three-dimensional space. To understand gravity, we must mathematically reduce this bridge for a vacuum state to find the exact exchange rate between the two domains. First, the topological ground state carries no extrinsic structure. This totally geodesic embedding condition zeroes out the extrinsic curvature terms. Next, empirical observation verifies the spatial manifold is isotropic. This map of the cosmic microwave's background shows temperature fluctuations uniform to 1 part in 100,000. Applying this isotropic condition simplifies the Ricci tensor term into ambient spatial curvature divided by 3. The intrinsic surface curvature equals the ambient spatial curvature minus 2/3 of that same ambient curvature. Inverting this remaining equation establishes a direct proportion. The ambient three-dimensional spatial curvature equals exactly 3 times the intrinsic two-dimensional surface curvature. Combining this inversion with the algebraic definition of a de Sitter vacuum defines spatial curvature as 2 times the observed cosmological constant. Substituting these terms reveals the final fractional interface. The observed vacuum energy equals exactly 3/2 of the topological surface curvature. This 3-to-2 factor is intrinsic to the polyhedral geometry, translating phase stabilizer dimensionality to edge stabilizer dimensionality. The standard vacuum energy formula links the energy floor to the cosmological constant and Newton's constant, g. By rearranging the formula algebraically, we can isolate Newton's constant. The numerator remains independent of g because the topological scale r is fixed strictly by the 3-to-2 curvature derivation. The denominator is also g-free, as the energy floor is independently sourced from the discrete mass spectrum via Reidemeister torsion. Newton's constant g is therefore a closed-form algebraic output. It is the exact cost of translating surface curvature into the energy floor the spectrum produces. This structural depth establishes a scaling law, assigning exponentially suppressed energy states based on hierarchy location. Dark energy occupies depth 2, the ground eigenvalue of the Möbius surface. Dark matter occupies depth 3, appearing as gravitational curvature within the space manifold. Detectors are limited by the fact that non-gravitational gauge fields only propagate in shared manifolds at depth 2 or shallower. Dark matter particle searches fail structurally because the depth 3 geometric sector is gravitationally active, while remaining gauge invisible. This bullet cluster image provides evidence for this depth hierarchy. Pink regions represent baryonic gas. At the shallowest depth, it interacts electromagnetically and decelerates. Blue regions map invisible gravitational mass, passing cleanly through the collision, separated from the gas. Pure depth 3 geometry possesses no scattering cross-section, causing it to structurally decouple and pass through baryonic matter exactly as predicted. Standard quantum gravity programs have consistently failed to unify general relativity with quantum mechanics. These programs assume homologous structures exist on both sides of the interface. Forcing the continuous space to discretize removes the exact geometric structure that sources the cosmological constant. Continualizing the discrete sampling domain dissolves the fundamental mass gap and particle generations. Space-time emerges as a four-dimensional coordinate chart, generated when an observer samples the underlying global standing wave. The resistance to quantization represents the mathematical signature of an interface doing work across mismatched topologies. Einstein's field equations provide the score. 3/2 provides the time signature.